Hello friends, welcome to my channel. Let's have a look at the daily challenge problem. That is problem 1448, count good nodes in binary tree. So in this video, we're going to practice some traversal algorithms in both iterative format and recursive format. So first, I'll read through the short statement, and then we do the analysis and share the codes. Let's look at the statement. So given a binary tree called root, a node x in the tree is named good if in the path from root to this x, there are no nodes with a value greater than x. So we're going to return or required to return the number of good nodes in the binary tree. So here are three examples. And example 3 is a trivial one or edge case. So because this is a single node tree, so the return should be 1. And let's look at example 1. So here the root is 3, so it's a single node path from root to itself. So this is a good node. And then if you look at the left subtree or left node, 1 is not a good one because 1 is less than 3. And then if we look at the left child of 1, so we get 3. There's no other nodes have value greater than 3, so this 3 is also a good node. So currently we have 2 good nodes. And then if we look at the right child of the root, we have 4. So in the path from 3 to 4, 4 is currently the largest one. So 4 is also a good node. And then if we look at the right node, right subtree of 4, that is 5. So 5 is currently the maximal. So 5 is also a good node. But if you look at the left subtree of this 4, so 1 is less than 4, so 1 is not a good node. So within these 6 nodes, so 2 of them are not good nodes, all the others are good nodes, so the output is 4. So similarly, we can analyze example 2. So we have 3, 3, 4. On this path, all the nodes are actually good nodes because the path contains or consists of increasing nodes values, or not decreasing to be more precise. So here the 2 of the right child of this 3 is not a good node because 2 is less than 3. So in this case, we're going to return 3. So with that said, actually we can look at the methods. So the methods or the solutions we are going to present or practice are all based on traversal. So we can do both breadth first search or depth first search. So it depends on how we use the container if we want to practice using iterative formats. Or we can write a solution using recursive format for depth first search, for example. So the idea is actually very simple. So for each node, we compare the node value with the maximal node values from root up to its parent. Let's call that value maximal before. Then if the current node value is no less than the maximal before, then this node itself is a good node. So we are going to increment the good nodes count by 1. So that's actually all. So our plan is the following. So first, we are going to practice iterative format. So we're going to use an iterative format of solution or solutions to demonstrate the details. And then we are going to write a recursive depth first search solution. So that's the plan. So now let's look at the code. So we're going to go over the code line by line. First, I'm going to write a iterative format. So for this, we can use either breadth first search or depth first search, depending on how we pop in the container. So I'm going to initialize something called container. So the container will store the current node value, let's call it root, and the maximal value before we look at this node. So here in this problem, so each node's value is in between negative 10 to the power 4 up to positive 10 to the power 4. So we can make it very small. Let's see, 10 to the power 4, I see minus 1. So as long as it's less than this number, it's okay. So we can initialize this to be say negative infinity. So here what we store is a node and the maximal value before we arrive at this node. So that's it. So notice that this is always not empty, because here the number of nodes in the binary tree is in the range 1 up to some number. So in other words, this tree is not null. So with that said, so we can do the traversal. So first, I'm going to initialize a result variable whose final state is what we want to return. So this container, we can use it as a queue, which corresponds to breadth first search, or we can use it as a stack, which corresponds to depth first search. So it depends on how we do the pop. So with that said, let's do the while loop for the traversal. While container. So then we're going to get the current node. We're going to look at the maximal value before this node. That is container pop. So if we pop from the tail, so we're going to use it as a stack. So this corresponds to depth first search. So if we pop 0, so this corresponds to a queue. So we're going to implement a breadth first search. So I'm going to use pop from the tail of the array, mimicking the depth first search. So then what we're going to do is that we examine if the node we are currently looking at is a good node. So the condition is node value is no less than the maximal before. So in other words, we check if node value is greater than or equal to maximal before. So if this is the case, we're going to increment the result by 1. And then what we are going to do is going to include the possible children of this node. Then we're going to update the maximal before to be the maximal of maximal before the previous state and the node value now. Just for preparing to put the children of the current node into the container. So now let's look at the children. So if node left also or right, so let me first write right. So in this case, what we are going to do is that container append. So we are going to add this node right, and the maximal before is this state, right? So maximal before. So this is the one case. Then we're going to check the left child or left subtree. Then we're going to copy this line of code. Then let's change this to be the left. So this maximal before is the same, because this maximal before is the maximal node value before the node right or node left. In other words, up to their parent's node, right? So that's the procedure. So after this while loop, actually the final state of the result is what we want to return. So that's a standard traversal solution. So because here we append the container from the tail. So if here we pop from the tail, so actually this solution corresponds to a depth first search. And if we pop from 0, it's corresponding to a breadth first search. So with that said, let's first examine a special case. Yeah, it passes example 1, I guess. So now let's look at generic case. Yeah, it passes all the generic cases. So this format of solution is iterative. So now let's look at another format of solution. I'm going to copy this function signature and change this one to be a v1. And then we're going to do a recursive solution. So for recursive solution, it's very convenient to implement depth first search. So for that, I'm going to initialize a variable. So let's say or attribute called self result. So initially it's to be 0. So this way of writing is just for convenience of updating this result. So I'm going to define a hyperfunction. So define a worker or hyperfunction to update self result. So I'm going to call this function depth first search. So we're going to pass 2 values. One is node, one is maximal before, right? Then let's do the check. So the first base case is actually very simple, corresponding to this case. So that is, we check if the node itself is a good node. If node value is larger than or equal to the maximal of 4, then we are going to increment the self result by 1. So this is one case. So another case is that after we do the base case, we are going to check if the node has left subtree or right subtree. If so, we are going to traverse the left subtree and the right subtree. So for this, let's check if node left. Then we are going to traverse the left subtree. So we're going to do DFS node left. So the maximal value before or up to the parent of node left, in other words, up to node, is nothing but maximal of maxi before and node value. So this is one case. And then we're going to check if this node has a right subtree. So let's copy this and change this to be right, and also change this to be right. So this value or this state does not change because the node right has parent node same as node left, right? So the maximal before should be the maximum of the pre-state maximum before and node value. So with that said, actually this we finished the writing of the hyperfunction or the worker. So what we want to do actually is to actually call the worker, that is DFS, so node. So we want to put a value, so maximum before we look at the root. So here we should put the root. So because of the range here, so the range is negative 10 to the power of 4. So we can put the 10 to the power 4 minus 1. So this way, actually, after we execute this function, so the attribute result is updated. So what we are going to return is nothing but self result. So this is another format of solution. So in a recursive format. So let's do a special case check first. Yeah, it passes the first example, I guess. So now let's do a generic case check. Yeah, it passes all the generic cases. So I guess that's about it for these two formats of solutions. So one in iterative fashion and the other is in recursive fashion. Actually, both the two formats are based on traversal. So this actually is some sort of routine practices. So with that said, I guess that's about it for this video. Thank you very much.